The objective of this lecture is to provide an introduction to kinetics of particles. Kinetics is the study of motion of a physical system that arises due to actions applied to the system. In the case of mechanical systems, kinetics is the study of motion of systems with mass that arises from either forces or moments applied to the system. The first part of the study of kinetics is concerned with kinetics of a single particle. A particle is defined as a point in three-dimensional Euclidean space with mass. That is, a particle is a point mass. In this part of the material, models will be developed for actions that arise commonly in dynamics. Then the laws of motion for a particle will be described. Using these laws of motion, together with the models developed for commonly used actions, equations will be derived that describe the motion of a particle of interest. And that basically means that examples that will be studied. Now, so the first part here is to develop models for commonly used actions. So for a particle, the constituent action is that of a force. So in this first part, we will develop models for forces that commonly arise in dynamics. So this is the first part of this material. Models for forces that commonly arise in dynamics. Now, there are lots of different types of forces, but we're going to be focusing on three. So these are three representative classes of forces. The first one are what are called contact forces. The second are linear spring forces. And the third are gravitational forces. And we're going to go through each one of them. Contact forces, which is the first category of forces of interest. Now, contact forces come in one of two different forms. One, a particle moving while in contact with a surface, and two, a particle moving while in contact with a curve. Let's start with a particle moving while in contact with a surface. So a particle moving while in contact with a surface. So here's the setup. Let S be a two-dimensional rigid surface in E3, three-dimensional Euclidean space. And this surface is such that there's a particle that's sliding on it. So let P be a particle of mass m that slides or that moves while in contact with the surface. So under the assumption that S is a rigid two-dimensional object, a rigid two-dimensional surface, S is a reference frame. Now we're gonna need a few things in order to be able to make this work. So to be able to develop this model. So the first thing is that the surface itself is graphically described as follows. Put this on the next page. So here's my surface. And actually, let's go a little bit more. And we're going to call this surface, call it S. There's a particle of mass m that's sliding on S. So here's a path that's subtended by this particle. And as the particle moves, at some point in time, it's located at point P, and it's a particle of mass m. Now, if you look, you'll see that S is a two-dimensional surface in 3 dimensions. And we need a couple of things in order to be able to make this, to develop this model. So because P is in contact with S, S exerts a force on P. This force is given as follows. We call it Fs, which is the force exerted by the surface on the particle, and it's decomposed into 2 forces, N and F sub F. N is what's called the normal force. It's also called the reaction force. Exerted by S on P. And F sub F is what's called the friction force. Now, in order to be able to see what these 2 forces are, I'm going to draw on this picture a plane, which is the tangent plane to the surface at point P. So this plane here is the tangent plane to S at point P. And I'm going to abbreviate that as TPS. Now, the force N lies along the line of action orthogonal to this tangent plane. The friction force lies in the tangent plane. So let's suppose we let N equal the normal, or I should say the unit normal to TPS. then the reaction force can be written as some component n times this direction normal. Now, what is this direction normal? So the first thing we need to figure out is what this vector little n is. So from vector calculus, the direction normal to a surface lies along the gradient of the function that describes the surface. In this case, the surface S can be described by a function of the form f of r equals 0, where r is the position of a point on S measured from a point O, where O is fixed in an arbitrary reference frame A. So what that means is that if I have an arbitrary reference frame out here, I'll call it A, and I have a point O, and O is fixed in A, then this surface, there's a set of points. I can just call these points defined by a position. And the point I'm really interested in is the point where the particle is located, because I'm going to, as the particle moves, it moves to different points on the surface. But in general, there's going to be a set of points or a locus of points that defines this surface, and those points are going to be defined by the function f of r equals 0. Now, given that I have that setup, then the vector n, which is normal to TPS, is given as n is equal to the gradient with respect to r of f of r, all divided by the magnitude of the gradient of r, gradient with respect to r of f of r. So that gives me the model now for the normal or the reaction force in terms of the direction n, which is in terms of the gradient of the surface. So next, the friction force has the form that is equal to some coefficient times VPS. And what is VPS? Where VPS is the velocity of the particle P as viewed by an observer fixed in S. Now remember that I said that S is a reference frame, so that's a well-defined quantity. The velocity of point P is viewed by an observer fixed in S. Now, once I have that, velocity, then and I say the friction force, as I said, is equal to some some coefficient b times that velocity, what I can do now is I can do this with two different friction models. So two common friction models. One is what's called Coulomb friction, and the other is what's called viscous friction. Now, let's do Coulomb friction first. Coulomb friction, which is also dynamic Coulomb friction because I'm dealing with motion. The model is as follows. F sub f is equal to minus a constant, which I'm going to call mu, times the magnitude of the normal, times VPS, all divided by the magnitude of VPS. The next model, which is the second possible type of friction that we're going to be dealing with in these studies, is F sub f is equal to minus C times VPS. This is viscous friction. These two different models arise in different situations. Sometimes for a system, an appropriate friction model is a Coulomb friction model. In other cases, it's a viscous friction model. Viscous friction is also often called damping friction. It's what you might know of as a viscous damper. We call it a viscous damper, and it has that form. So in any case, you can see that both of these are linear in VPS. So, well, I mean, there's a coefficient that arises. In the case of Coulomb friction, what we have is we have this coefficient B is equal to minus mu times the magnitude of the normal divided by the magnitude of VPS. In the case of viscous friction, B is just equal to minus C. So now we have models for viscous friction and Coulomb friction for a particle sliding on a surface. And again, we'll just remind that the force exerted by the surface is equal to N plus F sub f, where N is equal to N times the unit vector normal to the surface, and that vector, N, is the gradient with respect to R of the function that defines the surface divided by its magnitude. And F sub f is equal to some coefficient B times the velocity as viewed by an observer fixed to the surface. And F sub f takes one of two forms. It either takes the form of minus mu times the magnitude of the normal times VPS divided by the magnitude of VPS. And this is for the case of Coulomb friction. And then minus C times VPS. And this is for the case of viscous friction. Now, we've dealt with both of those. Now we're going to move on to a particle sliding on a curve. So the next case is a particle moving while in contact with a curve. So in this case, we have a slightly different setup. Let C be a one-dimensional curve in three-dimensional Euclidean space. And assume that C is not a straight line. As if it's a straight line, things degenerate, and that exception has to be handled separately. It's not hard to handle, but but it has to be handled a little differently. So then, under these assumptions, assuming that C is rigid, C is a reference frame. So now we have a reference frame just like we did before. So what does this picture look like? So here's my curve. And this is a rigid curve. Call it C. And at some point on this curve, there is a point P, which is my particle of mass m, and it's moving while in contact with this curve. So P moves while in contact with the curve C. So now what I'm going to do is I'm going to draw an intrinsic basis relative to the curve. Remember that we had studied intrinsic coordinates when we did kinematics. I'm going to start with an intrinsic basis and then define the forces, or the force that's exerted by the curve on the particle. So because P moves while in contact with C, C exerts a force on P. And this force has the form that Fc is equal to n plus F sub f. It has the same form as what happened in the case of a surface, but now these forces are actually going to be characterized differently from the way they were before. So this basis, which I've drawn, is an intrinsic basis. ET, EN, EB is an intrinsic basis relative to the curve C. And I'm going to use that intrinsic basis to be able to define the forces, but I'm going to define them in the opposite direction from the way I defined them before, meaning I'm first going to define the friction force, then I'm going to define the normal force. So the first thing to note is that, again, these forces are the same, have the same nomenclature as what was used before. N is the reaction force. Well, I should use the same terminology I did before. I called it the normal force, which is the reaction force exerted by C on P, and F sub F is the friction force. We're going to do the friction force first. The friction force has the following model in the case of a curve. It's going to equal some coefficient b times the tangent vector. And that's the tangent vector to the curve. Now, there are two different friction models. Again, and these are the same two friction models that were discussed earlier. The first one is what's called Coulomb friction. And the second is what's called viscous friction. So let's do Coulomb friction. In this case, the model is as follows. The friction force is equal to minus mu times the magnitude of the normal times the tangent vector. So we know that the tangent vector can be defined in terms of the velocity as viewed by an observer relative to the curve. So I'll get to that in just a second. Let's write down the viscous friction model first. The viscous friction model has the following form. It's similar to what was done for a surface. It's minus c times the velocity as viewed by an observer fixed to the curve. But now let's look over here. The velocity VPC as viewed by an observer fixed to the curve. So it's the velocity of P as viewed by an observer fixed in C. And that velocity can be written in terms of the intrinsic basis as the speed times the tangent vector. So this gives me that the viscous friction force can be written as minus c times the speed relative to the curve times the tangent vector. Now that gives me both friction models for the case of a curve. The next thing I need to do is I need to describe the reaction force. In this case, N, which is the reaction force, has two components, N sub N En plus N sub B times EB. Now you'll notice that if you go back to the picture over here, you'll see that I drew this intrinsic basis. So and you can see that given the fact that N has two components, one along En and one along EB, that means that N lies in the En-EB plane and is orthogonal to f sub f, because f sub f lies along the tangent vector. And so we wind up with a similar situation from what we wound up with in the case of a surface. In the case of a surface, the reaction force was in the direction normal to the tangent plane at the location of the particle, and the friction force was in the tangent plane. So in both cases, the normal force and the friction force are orthogonal to one another. In this case, the normal force lies in a plane that's orthogonal to f sub f, and f sub f lies along the line of action of the tangent vector. So to summarize the case for a curve, just like we did for a surface, remember for a surface we summarized all this. Let's do it again. So let's put down all the sort of relevant salient features here. The force exerted by the curve is equal to the reaction force plus the friction force. The reaction force lies in a plane that's spanned by the vectors En and Eb, where En is the principal unit normal to the curve and Eb is the principal unit binormal to the curve. The friction force comes in one of two different forms. In the case of Coulomb friction, we get minus mu times the magnitude of the normal times the tangent vector. This is for the case of Coulomb friction. And for the case of viscous friction, we get minus c times the speed relative to the curve times the tangent vector. And this is for viscous friction. So now we've completed the discussion of a particle moving while in contact with either a surface or a curve. The next type of force that I want to describe, or category of forces, are what are called linear spring forces. So the setup for linear spring forces is as follows, is that suppose I have a point Q, And emanating from Q, I have a spring. And at the other end of the spring is a particle of mass m. The spring is a linear spring. Now, what's characteristic of all linear springs is that they have spring constants, which are called K. I'm going to define the length of the spring here. I'm going to define it as L. And I'm going to start using these parameters to define the force in the spring. So K is what's called the spring constant. And L is what's called the length of the spring. And you can actually see that from this, if I say, look, we can do this in just in 2 steps if you want to, is that I'm going to define L naught to be the unstretched, it's also called the uncompressed length of the spring. And I'm going to define RP relative to Q to be the position of P relative to Q. Now, let's get started with the spring model. So, for a linear spring, the force exerted by the spring on the particle is proportional to both the spring constant K and L minus L naught, where L minus L naught is the stretched, is the, say, the compressed or stretched length of the spring. Now, there are 2 cases for the spring. The spring can either be stretched or compressed. So let's take case 1. Case 1 is compression. Now, in the case where the spring is compressed, that means that L is less than L naught. In this particular case, we know that the force in the spring is proportional to both K and L minus L naught. That's what I said for a linear spring. But if you look at the picture, you'll see that if the spring is compressed, it means that the force has to be along the direction from Q to P. So that means that but L minus L naught is negative. So if I want this force to be along the direction from Q to P, then it has to lie along the direction as described. Let's look at this. So RP relative to Q divided by its magnitude defines the vector, unit vector, along QP. And L minus L naught is negative. So given that L minus L naught is negative, if I want the force to be along the direction from Q to P, I have to put a negative sign in front of the result. So I get that result for the case of compression. Case 2 is what's called extension. And this is when L is greater than L naught. Now, in the case of extension, let's go through this again. So let's look back at the picture. And we can see that in the case of extension, if I extend the spring beyond its unstretched length, then the force has to be along the direction from P to Q. So given that, again, the force is proportional to K and L minus L naught. But now, if I use this vector from Q to P again as my unit direction, then now the force, now L minus L naught is positive. So in order for this force to lie along the direction from P to Q, there has to be a negative sign that is introduced to be able to get the model to come out correct. So in both cases, I get the same result. I get that the force in the spring is equal to minus K times L minus L naught times the position of P relative to Q, all divided by the magnitude of the position of P relative to Q. But we can simplify this a little bit as follows. Suppose I let US equal the position of P relative to Q, all divided by its magnitude. Now, if you look back at the diagram, you can see that the length of the spring is actually equal to the magnitude of the position of P relative to Q, which gives that US is equal to RP relative to Q, all divided by L. From which I can then write that the spring force can be written as minus K times L minus L naught times US, where US is the vector that I defined, which is the unit vector along QP. So this is equal to the unit vector along QP. Now, if you go back over to the diagram here, let's label this. Q is what's called the attachment point of the spring. This is what's called the attachment point of the spring. So basically it says that the spring starts at the attachment point, whatever that point is. So I can actually add that in up here if you want. Q is equal to the attachment point of the spring. And so therefore, US is the unit vector along QP, where Q is the attachment point. Okay, so that takes care of linear spring forces. We have a model now for a linear spring force. The third type of force, which I'm going to be studying here, are what are called gravitational forces. Now, gravitational forces work as follows. I have two particles of mass m1 and m2. I'm going to define the vector from m1 to m2 to be r. So r is the position of 2 relative to 1, which is the vector from m1 to m2. Now, the force of gravitation between these two objects is defined as F sub g. So F sub g is what's called the force of gravitational attraction exerted by m1 on m2. And it has the following model. It's equal to a constant minus a constant g times m2 times m1, all divided by the magnitude of r squared times the unit vector along the direction from M1 to M2. Now, in order to make this a little bit more tractable as an expression, I'm going to say let scalar r equal the magnitude of r, and ER equal the vector r divided by its magnitude. So then, the force of gravitation can be written as minus g m2 m1 all divided by r squared times ER. And this is, again, the force exerted by M1 on M2. So if we do the reverse, given this, the force of gravitational attraction exerted by M2 on M1 is minus Fg. I just reverse the entire process, and if I do this from M2, I get the exact opposite of what I get from M1. Now, there's a special case of the force of gravitational attraction. It turns out that this constant G, before I finish, is what's called Newton's universal constant of gravitation. Okay. Now, there's a special case of this, which is what's called the force of gravity. Force of gravity. And this works as follows. It's an approximation. Is that let M be a particle, or I can say it this way, let P be a particle of mass M in close proximity with a very large massive object. Now, let the large massive object be a sphere of mass capital M and radius capital R. So here's what this picture looks like. I have a sphere, and the sphere has a radius R. So there's the center of the sphere. So the radius of the sphere is R. And there's a point P, which is my particle of mass M. And let's let the center of the sphere be O. And this is point P. This is my particle of mass M. And it is located in close proximity to the surface of the sphere. So suppose I let this point Q, I'm going to label a point Q. Q is on the surface of the sphere. So Q lies on the surface of the sphere. And the distance from Q to P, whatever that distance is, I'm going to call it H. So H is the distance from Q to P. Now remember that the radius of the sphere is R, so the distance from O to Q, that distance is R because Q lies on the surface of the sphere. And I'm also going to put a plane here, which is because I'm going to need it a little bit later. So let's move this R over here. And I have a plane. This plane is the tangent plane to the sphere. So this right here, this is the tangent plane to the sphere at point Q. Which again, I remind everyone that Q lies on the surface of the sphere. Now, if we do this, I'm going to define one more vector. I'm going to define the vector along OP, the unit vector. I'm going to define that unit vector to be ER. It's the same unit vector that I had before. The mass of the sphere is big M. Now we're going to make an assumption. We're going to say, assume that the entire mass of the sphere is concentrated at point O. And that means basically now I have the equivalent of two particles, except for the sphere itself is massless except for at one point at its center. So if I write the force of gravitational attraction exerted by, I'm going to call this the force of gravitational attraction exerted by the sphere on the particle now this, if I use the terminology that I did before, gives me minus g times the mass of the particle times the mass of the sphere, all divided by r squared times er, where in this case r is equal to capital R plus h. Now assume that h is much, much less than r. What that means is that the particle is in close proximity to the surface of the sphere. Now, given that, that means that h over r is much, much less than 1. So then, we can write the following. I can actually make one more step here before we write this, which is that r can then be written as r times 1 plus h over r. So, saying right, say we can make the following approximation. So here's my approximation. That r squared, which is equal to r squared times 1 plus h over r squared, can be approximated as just r squared, because h over r is much, much less than 1. As a result, the force of gravitation applied by the sphere to the particle can be approximated as minus g times m times big M, all divided by r squared times er. Now let's return to this tangent plane for just a minute. So remember that there's a sphere, and there's a point Q on the sphere, and that's the point where this particle, if you draw the line from O to P, the point Q lies along the line from O to P and is on the surface. So if I put Q there afterwards, if I draw this plane, here's the plane that's tangent to the sphere. I'm going to redraw this plane call this point now Q. I'm going to redraw this plane this way. So here's point Q, here's point P, and then point O is somewhere down here. There's point O. So this direction from Q to P, this is P, the unit vector in that direction is ER, because it's the same unit vector that's in the direction from O to P, because Q is along the line from O to P. So what we can do is, this plane, which I've just drawn, this tangent plane, this plane is what's called the local horizontal plane. And it's the tangent plane to the sphere at the point that I'm interested in. It's the local horizontal plane. The vector ER, this vector, is what's called the local vertical, or the local unit vertical. And we normally call that direction something else. We say let UV be the local unit vertical, which from the diagram is the same thing as ER. So then we can write the force of gravitation. It can be approximated as minus G, and I'm going to make a rearrangement here, minus G times M over R squared times M times ER. And I'm going to put this quantity here in brackets. The quantity G times M over R squared is called the local acceleration due to gravity. Now, it's only true if the particle is in close proximity to the surface of the sphere. If it's not in close proximity to the sphere, then this doesn't apply. But we approximate this, or we call the terminology as it works like this. Let G equal Gm over R squared. And if I do that, then the force of gravitation will approximately be minus mg times uv. Now this is what you normally associate with gravity when you're dealing with sort of an approximation of a flat planet or a flat Earth. When you're dealing with the Earth, is that there is the local horizontal plane, and we normally write that if this is the unit vertical, that mg acts in the direction opposite the local unit vertical. So we say that mg, which is the force of gravity, it's also called the local force of gravity, is equal to minus mg times uv. Notice that we don't call it the force of gravitation anymore. We call it the force of gravity because we've made an approximation that the gravitational force is going to be replaced with this approximation, which involves this quantity little g, and that now changes the terminology slightly. It becomes the force of gravity, and gravity is the local approximation due to the fact that I'm in close proximity with a particular point on the surface of the sphere. Now, we can actually compute this for the Earth. Let's actually do this. So suppose we compute, and of course this is an approximation, so approximately the value of G for the Earth, assuming that the Earth is a homogeneous or uniform distributed mass sphere. That's what I mean by homogeneous. It's a uniformly distributed mass sphere. So let's pull a few of these numbers from a common place. Let's go look and see what these numbers are. So the radius of the Earth, if you take the equatorial radius, is 6,378,137 meters. That's approximate. The mass of the Earth, so the mass of the Earth is equal to 5.9723 times 10 to the 24th kilograms. And then Newton's universal constant of gravitation is equal to 6.67408 times 10 to the minus 11 meters per kilogram seconds squared. And these, of course, are all approximations. So if I plug in to G, I get G is equal to capital G times M, all divided by R squared, which is equal to 6.67408 times 10 to the minus 11 meters per kilogram seconds squared times the mass of the Earth, which is 5.9723 times 10 to the 24th kilograms, all divided by 6,378,137 meters squared, which results in G is approximately 9.79219 meters per second squared. Now, you may actually recall that commonly what's used as the the acceleration due to gravity, G is commonly taken to be 9.81 meters per second squared. So using these approximations, which I pulled off of the web, we get pretty close to 9.81. Now, the value 9.81 is more accurate because the Earth is actually not a homogeneous sphere, so it's not uniformly distributed mass. The radius is not exactly what I got, because the radius changes because the Earth is actually not a sphere. It's actually an oblate spheroid. But that's fairly close. So we got a number that's pretty in line with what you would get if you just use the standard number of 9.81 meters per second squared. So in summary here, the force of gravity is an approximation, and we call this approximation mg. And mg has the form minus mg times uv, where uv is what's called the local unit vertical, and g is what's called the local acceleration due to gravity. So, in summarizing this lecture, let's go through the following. Again, is that we've developed some models for commonly used forces have been developed. These forces are contact forces, where the contact force is divided into normal force and friction force. Models were developed for friction, so two common friction models were developed, and those friction models were Coulomb friction and viscous friction. And contact forces were developed for both surfaces and curves. So that means a particle moving while in contact with a surface or a curve. The second class of forces were linear spring forces, and the third class of forces, which I just finished, were gravitational forces. Now, in the material that's going to follow, we're going to use these forces as part of, in conjunction with the laws of motion, which I'm going to describe shortly. And then, once we describe the laws of motion, we're going to start applying this framework that we're building, which has the force models together with the laws of motion, to be able to describe motion or determine the equations that describe the motion of a particle of interest in a system that we're going to be studying, which will be studied through different examples.